Morning everyone, I'm Wei Tan, a senior lecturer from Queen Mary University. Today I'm very pleased to present my recent work on failure modeling of composite materials. One key question I want to address is what is the role of moisture on the mechanical properties of composite materials? Before I dive into the details, I'd like to thank my students and my collaborators for making excellent contributions to this work. Let me start with the motivation. Offshore energy offers a vast and renewable energy resources, including wind, tidal, and wave energies. The annual global investment in offshore energy is expected to reach 100 billion by 2050. By that time, the offshore energy can supply over 35% of the global electricities. This highlights the enormous potential of offshore energy in our green transition. However, there are some problems here. One of the main challenges is to develop resilient materials for offshore energy. As you know, lightweight composite materials have been widely used in wind turbine blades. In service, the turbine blade can experience very extreme weather conditions, including the combined moisture and temperature effects. This including some extreme loading case like high velocity impact of liquid can cause rapid wear of the wind turbine blades. Typically after 3 years, you need to send people to repair the wind turbine blade. Therefore, think about the cost. Repairing this is really expensive and it could grow from 80 million per year to 25 times larger. So therefore, it highlights the need to develop a fundamental understanding on this moisture-driven damage. What are the possible mechanisms? From the experimental observations, we can hypothesize that moisture can cause the swelling of the matrix. It can also lead to matrix plasticizations and hydrolysis. This could also introduce some fiber matrix debonding. The challenges here is current experimental results typically can only offer the insight at the homogenized level. If we want to track the microscale damage initiation and evolution, this is super challenging. So how are we going to review that damage? This needs a very powerful combined experiment and a computational model to help us understand the underlying mechanisms. The state-of-the-art modeling in these areas typically remain relatively unexplored. In the paper published by Orange in 2022, the moisture diffusion was not modeled. Instead, they assume uniform distributions on the material. We will try to present a multiphysics models to incorporate the moisture diffusions. In other recent papers, people have argued a cohesive zone model is really difficult to predict the diffusion across the fiber matrix interface because this is sharp interface nature. And also people observe in the experiment the material property across the fiber interface and matrix has a transition. Therefore, our model tends to address these issues by using new phase field models. I will come to that later. So how we are going to implement all these new elements? First of all, we want to present a fully coupled multiphysics phase field models to capture the interplay between the moisture hygroscopic deformation and fracture. If the fracture can happen, the new open space can actually cause some certain influence on the diffusion process. It can promote diffusion as well. So let's move to the details in the modeling part. For the moisture diffusions, it follows the second Fick's law. Basically, it describes the rate change of the concentration is proportional to the diffusion coefficient and the gradient of concentrations. Then we can write the moisture flux. It describes a certain amount of moisture across the unit surface area. Here, the new element we introduced here is considering the hydrostatic stress, because this stress inside the materials can influence the material diffusion process. The higher the hydrostatic stress, the lower the amount of diffusion can occur. Following that, we can derive the balance equation, which is based on the mass conservation law. This relates the rate of the moisture change with the moisture flux through the external surface. Move to the deformation problem. The deformation problem basically means if the moisture is absorbed into the material, it can lead to the swelling of the fiber and the matrix. We need to calculate this hygroscopic strain by considering the expansion coefficients times the change of the concentration. In our Hooke's law, when we calculate the Cauchy stress, we need to exclude that hygroscopic strain. In addition to that, we also need to consider the moisture influence on the material properties, such as on the fractotoughness, on the Young's modulus and strength. Once that happens, we can model the internal stress inside the materials. Then we can look at the fracture problems. We are using a phase field fracture models for this scenario. Phase field model is basically a computational framework of the Griff's energy balance. One can write this equation into a variational form, basically integral expressions of the total potential energy. Minimizing this energy functional actually is very challenging because the sharp interface will introduce some numeric instabilities. However, we can use phase field method, basically replace the sharp interface by diffused regions. These diffused regions allow us to approximate the crack by a scalar factor like damage variables from 0 to 1. Basically, the whole domain can be represented by this damage. That allows us actually to rewrite these equations in a volume integral, and we can solve these equations by solve the global minimization problem. By doing that, we can easily find the crack, the location of the crack, and the extent of their damage. This will further lead to us to quantify the damage path and the following problems. The last things we want to consider here is the crack can actually increase the diffusion coefficient. In that sense, when the crack happens, the open area can serve as the weak spot to promote the moist diffusions. One last puzzle we want to fill is the interface. How we're going to model the fiber matrix interface here. Basically, cohesive zone model is assuming a sharp interface. In that sense, we want to model these fractures at the interface and also model the moisture across the interface. To do that, we use phase field method again here. We approximate this interface by diffuse regions so that we can actually easily couple the moisture transport problem here. And secondly, we can also use this phase field method to interplay the transition or the graded material properties across the fiber matrix interface. By implementing all of these four elements, now we can actually try to solve these problems. Let's look at the results. In experiment, people tend to age a sample into the water for a few days, and then take it out and do the mechanical loading. You can quantify the mode 1 and mode 2 frac toughness. As you can see in this graph, it's actually plot the frac toughness against the moisture content. Surprisingly, you can see the moisture decreased the mode 1 frac toughness, but at the same time, moisture can increase the mode 1 frac toughness. So why is that? What are the mechanisms here? What occurs? The first question we want to ask, what occurs just after moisture diffusion takes place? If you look at the experimental results, you can see some fiber matrix debonding occurs. And this is basically can be explained by this failure sequence. You have the moisture diffusion. This can cause internal stress due to the mismatch between the fiber matrix internal stress or their coefficients in terms of expansion. They can have different internal stress, and this can promote the interface debonding. That's the first things when we're doing. Before you're doing mechanical characterizations, already trigger some internal interface debonding here. Let's look at some case study. The effect of moisture on the mode 2 fracture here. We have used the properties for the flax fibers and the epoxy matrix. We have applied the boundary condition in two steps. Step 1, apply the moisture diffusion boundaries at the left edge and the notch areas. Step 2, apply the end notch shear loading. Now, looking at the results, moisture diffusion will trigger some initial damage. This initial damage serves as a weak point. If you apply the mechanical load, you can see basically the crack path is the coalescence of the matrix cracking and the interface debonding. Now, without moisture, you can see the pristine sample without moisture basically have more crack branchings, and the crack can have much diffuse regions. Looking at the quantitative measure of the force displacement curves, you can see these curves without the moisture shows a higher energy absorption. This means moisture can decrease the material toughness. So why moisture degrade second mode 2 frac toughness? As I said, the dominant failure mode is the interface debonding in such case. Because moisture can result more interface debonding, this can trigger a great stress concentration and trigger more shear cracks. Let's look at the case study 2, how we model the influence of the moisture on the mode 1 crack growth. This is the virtual single notch bending test, where we want to predict the frac toughness on the mode 1 case. To actually model this in the microscale features, we use an embedded zoom. Ahead of the crack tip, we use a small windows where we can put this tiny fiber and matrix in a random manner, and then we can model their interface as well. This will simplify the problem because outside that embedded zone you have all homogenized properties. Then we can apply the moisture boundary and consider diffuse interface. Then apply the second step, mechanical loading here. Now this is the video showing the results. On the left, we have the experimental result where the crack grows. In the middle, you can see this is the dry case where the crack grows through the fiber matrix microstructures. On the right, this is the wet samples and very similar patterns, but if you look at them together, that's the final snapshots where you can see the same amount of displacement you applied. For the wet sample, you have smaller crack extensions. Looking at the R curve, you can see the wet sample basically have a higher fracture resistance. This does means help us understand why moisture can promote the mode 1 fracture toughness. Because from that simulation, we can see most of the failure happening in the matrix. The dominant failure is the matrix cracking with some other amount of interface debondings. Because the moisture can lead to matrix plasticization, this can introduce crack tip blunting and contribute to more energy dissipations. That's why it can promote the mode 1 fracture toughness. In summary, we have presented a new multiphysics framework to model the moisture-induced degradations in composite materials. A novel diffuse interface approach is presented to model the diffusion across the fiber matrix interface. Our model reviewed the dominant failure mechanism in the mode 1 and mode 2 failure. Our future work will focus on conduct more micro-scale experiments under environmental conditions and also extend the framework to model a large-scale structures. To conclude, I want to list some key references and our open source research code. Thank you for your attention. I'm happy to take any questions.